So it's 6, but let's wait a couple of minutes for folks to trickle in. So unfortunately, Zoom doesn't have the mingle mode. Usually meetups when we used to have them in person, right? This is the time people mingle, and we have the opposite problem of getting people to actually sit down. Okay, it's 6:02 Pacific time. I think we can start. I see a lot of folks coming in, and if folks miss anything, this is recorded and it will be up on the AI Cam website later, probably tomorrow, early tomorrow or something. Many thanks again, Bill and AI Cam folks for hosting this. They've been extremely great partner for us. Setting these things up and so on. So welcome to this meetup organized by the AI and Testing AI meetup group. So today we have Frank Fisher, who runs developer relations at DeepCode AI. .ai, and he's going to be talking about AI in practice in the area of modern code analysis. So a little bit about the meetup group. Who are we? So my name is Chris or Himing. I'm the chief instigator of these meetups. And we have, two very established advisors. One is Jason Arbon, who co-wrote the book How Google Tests Software, and Ron Brashear, who's VP of at HPE. I think he's here today. I think I saw him on the attendee list a while ago. As usual, any meetup group, we're always looking for speakers, and hopefully when this whole COVID thing is over, we'll probably be looking for venues as well as sponsors for food. If you have any ideas, please reach out to me. I'm on the meetup group. Just reach out and suggest topics and people to speak. Last of all, I would like to thank my company, Climate, a division of Bayer Pharmaceuticals, for allowing me to do this, allowing me to spend some time to organize these meetups. So without further ado, I shall hand it over to Frank, who will tell us a whole lot about code analysis.
Yes. Okay. Thank you very much. Thank you very much for the introduction. Yeah. So my name is Frank Fisher, and I'm from a company called DeepCode, and you will see what DeepCode does. What does this has to do with AI and static code analysis and things in the upcoming few minutes. The talk is called AI in Practice because what we do is, so to say, taking ideas of the field of artificial intelligence, and this goes beyond the typical machine learning that we see a lot currently. I think if you're not living under a stone, you've seen a lot of things in the past few days in the press about the GPT-3 model and stuff like this. So all of this machine learning, all of this goodness is part of what we are doing, but we are extending it into what is called the good old fashioned AI, and I want to show you a bit how this works, how this feeds into the idea of code analysis. To start off, I want to show you a bit of the agenda that I have, or we have ahead of us. It's a lot. I think I have too much stuff. I hope that I can share the slides later with you so that you can see even things that we have to jump over a bit maybe. And also what I would like to do is I would like to get a bit of a feel on how good we are in certain aspects here. So the idea here is that if you can open this URL. We'll not collect any personal data. You can do this in whatever browser with whatever privacy settings you want to have or so. It's just to get an idea on the level of knowledge that we have. Where do I have to dig a bit deeper? Where can I, so to say, slide over things because you already know this? And the results are here. Okay, so yeah. I see you're pretty well aware of these things of coding. That is good. Yep, perfect. Maybe one more vote or so, just to get an idea. I leave the. This is the. Where is it? So this is the URL. Okay. Yeah, I think that answers the big question that I had, and it is obvious, and I think I don't even have to look at the second answer because it's obvious. You are pretty well aware of coding. You know what we're talking about. That is perfect. So I can move a bit faster in certain aspects. Okay, so let's get into it. About us, about me. Who's DeepCode? What are we doing? DeepCode is a startup found in 2016. We had a seed round now, and we are preparing ourselves for Series A. It is actually a spin-off of the ETH in Zurich. And I think if you are a bit in the academic space, you know ETH, you have heard of that. Within Europe, it's one of the most prestigious universities for computer science. And actually, this is where we come from. This is our, so to say, lifeblood. The majority of people you see dancing here are actually people coming out of the ETH Zurich. DeepCode itself is based on research that is done within the ETH. Roughly a decade of research flew into the product in various aspects. And the basic idea that we had is that we want to unlock the big code. So unlock the code that is available in open source like GitHub repositories to help building better models, building better infrastructure for static code analysis, or as the academics would say, static program analysis. I use code analysis because it's a kind of a more often used term, but in the academic world, we're talking about static program analysis. Who am I? My name is Frank Fischer, as already said. I think I'm like 25 or 30 years now in IT. I worked for companies like Microsoft, Google, in Europe also a bit better known, the Deutsche Telekom, so the T-Mobiles of this world. So in large companies as well as in startups, as I'm now working in DeepCode. I have a master. I have two masters, one in physics and one in IT, and hopefully in 2 months from now I can proudly say I have a third master in organizational psychology. So I'm currently working on this one. Yeah, so I think that's enough of me. Let's get into it. Just a little bit of like motivation. Why are we doing this? I found this one quite nice, the F-35, and it's one of the projects that obviously show more software bugs. They are reporting software bugs faster, that they can close them, and I think it's not unknown. This is a very typical situation that you see in lots of projects in real life out there. And maybe F-35 was the one that was kind of the most prominent now because also of the size of the project and stuff. But I think it's a typical situation that we see all over the place. if we look now on these bugs and what are hard to trace bugs, and I want to do it here because it's easier to see and easier to follow. We will go into the tool later and you see then in real life these things also. So this is a bug that is documented. It's actually one of the things that Facebook found. Also our engine finds this bug. And what is behind this bug now? What you see here is this is live code. It's coming from the DuckDuck Live search engine, and what you see here is Java, and you see like a sequence of functions that calls each other. And what is the problem with this now? Let's follow what happens. So here we have a call to select feed by ID. So in this line here, we jump into this function here, and you can see the function sets the parameters. They initialize the parameters with the value null. So this is the initial value that we have. Now what they're doing is they're doing a database query. Then they go to move first and set the parameter here, set this variable to the feed object that there is, and they have a final. So there's try catch and there's a finally. So they want to make sure that the database query is nicely closed before moving on. The interesting thing now is that here is an if c move first. And the point with this is what happens if you do this query, but actually the query is empty. If the query is empty, move first here would result in a false. It would result in a falsy value. It would simply say, there is nothing. Yeah, there was no move first in that regard. If this happens, you will never get out to be set, and out will be set to null. So you will keep the value null on out. You return out, and this means now out becomes, or feed object becomes what out is, and this would be then null. What happens next is we are calling now this function down here with feed object, and this could be null. And if you see what we do here is feed object.getURL, and if this is a null, we have a null dereference. Yeah. The interesting thing now on this kind of bug is, number one, think about it. You know, you have 800 something lines of code in this file. This would be really hard to trace because you have to, you're jumping around. You see, it's really hard to follow the code in that regard. Another thing is that while you're doing dynamic testing, in the dynamic test, you would need to have the case covered that your table is actually null. Your table is empty. Sorry for that. Your table is empty, so that you get with a null here. If you don't have this in your test set, your dynamic testing won't show this. It's all valid code. You know, there's nothing that is wrong with this or something. So it will compile. And if the situation comes up that this table is actually empty, you can run into this problem in real life, in production in that regard. And what you see here is one of the strengths of static code analysis is we are not testing certain paths through your code, which is the typical dynamic testing way. We are actually testing, so to say, the whole solution set that you can have. All paths are tested. So one of the possible paths could be that this becomes null, and then you have the problem here. What does this mean now? And it's quite interesting to see the impact of this. I mean, I know you're practitioners, you're part of this industry, so you know from your personal experience how this is. Here is some data on how this really impacts. So there is the CISQ, the Consortium for IT Software Quality. This is a 2018 report, so it's pretty recently. And the report says the cost of poor software quality in the US 2018 is approximately $2.84 trillion. And just to give you an idea, the GDP in the US down here, yeah? So that you can see, you know, this is like 10% on the GDP or something. So this is huge. We're talking about huge numbers here. Here you have the breakdown where these things happen. Finding, fixing defects is a big thing. Losses of software failures, I guess that is pretty related to this. So you see there, it's huge numbers we're talking about here. So if we're talking about software quality, where does, so to say, this code quality come into play? And I just took the ISO standard, the 25010 standard here, and you see this standard says this is all part, these boxes are part of what we call software quality. And I took usability out a bit. We can argue also usability is part of good software quality, good code quality, but in the end all of the other boxes are for sure related to the quality of the code that we are doing. So the point that I want to make here is it's a big problem. It is something that we need to address. It is an inherent part of the quality of the product that we are generating here. Now, if you think about code quality and you think about best practices in code quality, there are some tools that you can use, revision control, testing, etc. We will focus on the static analysis today. And there's another reason why static analysis is so important in this regard, because it sits very early on. So this is the life cycle of software and where bugs can happen or where bugs can be found and then be addressed. And what you see is that the later you go into the life cycle of your software, into the development life cycle of your software, the more the bug costs. So fixing the bug in the later part of the life cycle is more expensive than really early on. And what you see here with static software analysis is that you static code analysis, that you're really early on here. You're in the prototyping, development, compiling part of it. So here, and this means you are very early on. It's the cheapest moment that you can find it. So it makes actually sense to have this and to run this. Okay, now diving into the static analysis technologies that we have, and there's a little curve here that we have to sort of say live with, and this is that if we are doing shallow analysis, we are very good in performance. So time memory is very easy on shallow analysis, and I will show what shallow analysis and deep analysis means in a second. Versus the more deeper I go, the higher the time and memory aspect the tool will ask from my environment gets. So the higher gets this. And what I sort of say trade with this is the precision and the recall. So the idea with this is how many suggestions does my tool provide me? This is the recall. And how precise is this? So how many false positives do we have versus true positives? And if you dig really deep into mathematics, there is a basic fundamental law. Code analysis can never be 100% precise. You will always have false positives in there. That is a bit of a mathematical rule, and I can give you the background if you want in some white papers and stuff. So we always have to have to think how much suggestions do we do? Do we do a lot of suggestions, so a lot of recall? That would also mean a lot of noise and possible false positives. Or do we increase on the precision side, but this would mean we would probably also not find all of these issues. So this is the balance that you have to do in these tools. And then obviously, the more time I take, the more I get out of the real-time feedback that I can give to developers. And this is an issue if you think about, I met some developers that are telling me we have legacy code bases in 20 million lines of code, legacy code bases. If we run deep analysis tools on that, it takes us 12 hours to run this, which is obviously not something you can do live in your IDE. Then it becomes something that you have to do later on in later stages of the development process, which makes it again more costly and stuff like this. So this is the idea here. So if we start now with like the most left side of it, there are some very easy tools, you know, that are literally treating source code as text. You know, a simple grep. If you look at Microsoft Application Inspector, it was a tool that was pretty hyped, like I don't know, 2 months ago or something, like 3 months ago. It is actually not doing nothing else than this. It's a very simple text tool. You can already do API misuse, depreciated APIs. You can search for authentication tokens. You know, when you have your AWS token in your GitHub repo and stuff like this. So this is doable. It's already usable, but it's very, very shallow. Then we go deeper into things like PMD, like ESLint, and here we start to use what is called the abstract syntax tree. So we are transforming code into an intermediate representation, and I will show a bit more about this in a second. And here you can go deeper. You can find local bug patterns. You can find already very interesting things. What do I mean with this? I mean this. So what you can do is you can, for example, say, this is a construction that we want to prevent. We want to use the dot equals construction in the compare strings because it is more precise. It is harder against bugs in that regard. So this is possible, but here we are already ending with these tools. So in this code, what we are doing here is we also have two strings. We are also doing the double equal, but we are calling functions on the two strings. And these tools, some of them know what is the return value of functions. Some of them don't, and there's the breaking point now. If we are calling functions on objects and stuff, what is the return type that is coming back? And it cannot defer this in some aspects. And to show you this, how this works, let me switch here. So this is PMD. This is the manual of PMD, or the documentation of PMD. And you see this is the equals to compare strings that I just showed. And how does this work now? What you see is what they're doing is they're using simple, so to say, queries. Here you can see the queries, and it's an XPath expression they're using here. So what this tool does is it takes your code, it generates an XML out of this, and it then uses XPath to run through this XML to find patterns that they're pointing out. And obviously, with this, you are kind of limited in the amount of things you can get out of this. Depending on how deep you crawl in the XML, how fine defined the XML is. We can go even deeper and use the abstract syntax tree and refined rule sets that are running iterations, for examples, where you start to build symbol tables, resolve names and stuff like this. There is an example called Arrow Prone that does this. With this, you can find things like that, where you return, for example, different types, or you return null that you want to trace, and you want to find null dereferences, for example. It's not 100% perfect. Yeah. So here again, we have the same issue. It would return null, but it might not follow the type of the variable here. That is what is would call be a point two analysis that it would have to be done, but it doesn't do this. So here we're getting a step deeper, but it still has elements that needs to be optimized. This is another thing. You know, here we have a call to a function that would give us possibly the null type, and we would have to follow this. What starts here is that you want to understand the intent of the developer. Yeah, you want to understand, is the null value something that is like a leftover of the language, or is it an intent of the developer and the developer wants to signal something with the null and kind of reacts on the null. And then there are extensions to languages. There is, for example, from Uber is a package called nullaway that gives you the opportunity to extend, to annotate your function, and says, hey, this function is actually capable to digest null values, or this function expects everything not to be null. And with this, you're getting in the opportunity to kind of help the system to follow the nulls and do things like that. The problem with this is you would ask to be annotated, to annotate your code, and obviously that is extra work. That is again a source of error where you could do the wrong annotations. So yeah, so we got stuck a bit in this, and this gives me, so to say, this, because the point that I want to make here with this is we have very sophisticated tools. We have very, so to say, mature tool sets in the C++ area, in the Java area, but still they're building up on things that were discovered and designed like in the 1970s, 1980s. So all of this is sitting on these kind of rule sets that were there, and these rule sets are developed by developers that scales linearly. So there was a bit of an issue with this. It didn't move forward as it should be moving forward. So here comes DeepCode. What I would like to do in the next step is I would like to give you a kind of a basic idea of what we're talking about when we're saying symbolic versus sub-symbolic AI, and then get into what DeepCode and others in that area are actually doing now to bring in these technologies into static code analysis. So let's start with symbolic AI. In the AI world, and I show this here with this little graph here. There were two main schools, if you want to put it this way. There was the symbolic and the sub-symbolic school. And actually, the symbolic is, if you want to say it, like maybe even the older of the two. As you can see in we're talking about 1950s here. So there was a big hype in symbolic AI. Then it kind of fall down, got out of fashion a bit in a way. And you see, the symbolic got up in the 80s here, and then it got down. This is the other color here. So not the red one. We are following this one here, the more yellowish one. So as you can see, it took off. It had very successful, and you will see what I mean with this when I do a demo. What does symbolic AI mean? But then the interest fell down, and in the 2000s and 2010s, the sub-symbolic AI really took over and pushed forward. And sub-symbolic is a term for describing machine learning, if you want to put it this way. So machine learning was literally pushing forward on the AI side, beginning 2010s with the neural networks and all of these things, major breakthroughs that were happening there, and it was pushing forward. And I think it is even so far that when you're talking to people right now, and you say AI, what they think is machine learning. For them, AI is equal more or less to machine learning, which is not true. It has these two aspects to it. The symbolic aspect is that we are trying to describe the world by using symbols. So we are recording facts, we are recording relationships between these facts, and then we are, from these relationships and from these facts, we're starting to deter more facts and more relationships out of the body of knowledge that we already have. This is actually in wide use already. So if you are thinking about what we saw with PMD and using these rule sets, that is not that far off of what we see here. If you're making a Google search query, you're actually using symbolic AI all of the time. When you're doing a search query and you see this little box on the side where Google has facts for the query that you had, this is actually a symbolic AI where Google started to collect facts of the knowledge base that we have there out of Wikipedia and stuff, and is trying to provide you these facts in combination with each other within the search results. So that this is there, and it's used all the time. Then we have the sub-symbolic part, and this is this side here. And as you can see here, we are talking more about probabilities. Yeah, so here we have the Bayes law there. So we are talking here about probabilistic view of things. and training a system with a lot of data into answering questions in a probabilistic fashion. And this is also the reason why you see the typical, so to say, ways of implementing and the pros and cons of the different fields. So for the symbolic AI, we're using symbolic programming, and I will show this to you in a second in a little demo. We are using then inference. There's the typical things, you know, prolog is one of the things, data log is another one. So these are the typical languages that you have there. And we're talking about rules and ontologies and plans and goals, so these things. On the sub-symbolic side, we have the learning side. So we're talking about deep learning. We're talking about neural nets and stuff. We have all of these typical machine learning algorithms. Symbolic AI is very good for building rules to introspect code. It is quite easy to debug because there are the rule sets, and the machine can literally tell you what rule set was fired to come up with the result that it came up with. It can explain itself. Yeah, we're talking a lot about explainable AI, and that AI needs to reason for what it does. Typically in the machine learning world, it is really hard to ask the algorithm why it came up with this. Yeah, because the weighting was like this. You know, you have a neural network that you trained, and even if you use the same data and you do the training again, the neural network might end up differently. And arguing why it came up with this idea is literally hard. There is no single argument for that. It's just that, you know, we saw this a lot in the training data, and so we picked up the pattern and now we're using it. It doesn't need to have big data. So symbolic AI does not need to have big data training sets. You can literally have maybe one example or maybe even no example at all, and you can still define a rule that is kind of picking up from here and is then bringing this into the body of knowledge that the system has. It's better for abstract problems where you have low noise, very clear definition of things, a very clear grammar and structure, yeah, very clear syntax of things. So here this is where symbolic AI kind of shines. The sub-symbolic AI needs data. Yeah, the more data, the better. It can cope easier with noise in the data. It can scale up very easily because it learns the rules itself. So it doesn't need to be trained on the rules, like coding the rules. It can be trained on the rules. So the big data part is of importance here. And it's also connected to neuroscience. So the idea that our brain works in a kind of the same fashion as this one with neural networks and stuff like this comes also in, which is interesting in certain aspects. For example, if you codify like natural language and stuff like this. So these are the two fields that there are. What we see now is these two fields start to come together, and this is what DeepCode is all about. And I think to kind of give you a better understanding of the symbolic AI stuff, I would like to do a little demo on this one. So here we have Swish. So this is Prolog, and what I would like to do is I would like to do a little program with you now. So I prepared something. What we will do is we will use this family tree here. So we want to tell the system this is the facts of the world. So let's start by giving the system some facts. Let's do that. So we copy and paste the facts here. So the facts are we have males, we have females, and we have a parent-child relationship. So James the First is the parent of Charles the First, and James the First is the parent of Elizabeth, as you can see here. So you see this here in this tree, and you see it here being codified into the facts of the world. Okay, so now the system already knows some facts and can already give us some answers. So I could, for example, ask, who's the parent? Charles the First. Who's that? Yeah, and if you run this, the system says James the First. So the parent of Charles the First is James the First. So this the system can already, so to say, yeah, reason about this. But now we can do more. We can literally say we are doing some more ruling. We're making some more patterns here. So we define what is a mother, what is a father. So a mother is if M, the mother, is female and M is the parent of X. Then the M is the mother of X. A simple thing in this regard, but I hope you get the idea that is behind. Or a sibling. A sibling is A and B are siblings when when the parent P is the parent of A and P is the parent of B and A is not B, obviously. So with this, we can start now to ask, for example, sibling. Who's the sibling of Charles II? So let's run this. And as you can see, Charles II has two siblings, Catherine and James. So Charles II, here he is, Catherine and James, two siblings. So the idea with this, and what I wanted to show you with this is the way how symbolic AI works. So we're defining a set of knowledge about the world. We are defining these rules, and then we can start to reason out of these rules that there are. A very nice example is this one, actually, to show how powerful the whole system can be. This is a Sudoku solver, and you can literally ask the system to solve the Sudoku here. And it does this only by knowing the Sudoku rules and reasoning out of the rules to find the final solution for the Sudoku play. So this is the idea now. And you also see the limitations in the whole thing. So number one, we need to have all of these facts of the world. Somebody needs to come up with these kind of relationships that we have here. So this is the goodness and the badness of the whole thing. We have to so to say work with these symbols and these rules of the symbols. Okay. So now currently what we see is there's a bit of a hype around the machine learning, so the sub-symbolic part on code. And what it does is it uses the source code. It so to say takes the same mechanism that we use for natural language processing by segmenting the text into different parts, and then using the same mechanism to kind of reason over it. And here I have this is one of the neural network forms that is used in these models. That is good and that is bad. The bad thing about it is reasoning over a probabilistic way of going forward to these things. And the probabilistic way is nice in certain aspects. So if I want to help you with code to complete your code in your IDE. So you start to type something and I want to make you suggestions on what could be the next word you want to search here. That might be helpful because actually there is a kind of a rule set behind it that is based in probabilistic parts. The problem in this is that code itself need to be 100% correct, otherwise it won't compile. And it is a creative art, if you want to put it this way. So there is some creative things coming in. So it is not as easily being trained into these kind of models in a probabilistic fashion. And we see the limitations that there are. If you want to generate code, for example, that actually compiles with a pure probabilistic way, it is really hard. And there is a lot of times where the outcome simply doesn't make sense. If you generate a Shakespeare sonnet, and it sounds a bit quirky, I think that is part of the deal. But if you generate Java and it does not compile, it doesn't help. So that is the issue that we are currently seeing with automatically generating code out of these kind of models alone. So the idea that we have is we need to go beyond that. But to go beyond that, to combine symbolic and sub-symbolic AI, and this is what I mean with going beyond that, we need to unlock one big thing to start with, and this is large code bases. There's a goodness to this, which is if you think about what we have now as code bases, and I found these nice infographics showing the growth of code bases over time. So we are talking about hundreds of thousands lines of code here. So the first Unix version was somewhere here. I very low because below the 100,000s, a few thousands line of code. And if you go now and you see where we are today, you see we are getting into here's the billion lines of code that we have, so to say, generated and we have to our command. The point that I want to make here is these lines of code, this goodness that you have here, this is actually nice training data. Yeah. So if we are thinking about introducing sub-symbolic AI into this, this is the training data that we can use. But if we are just using this training data as it comes, so we're using it as text, and we are training the sub-symbolic AI on the pure text side of it, we are losing the whole grammar. We are losing the whole syntax that is very, very nice in development languages and programming languages. We're losing all of this because we're treating it as pure text. You can do this. They are doing it. There are some tools out there doing it, but it doesn't unlock the whole thing about it, the whole aspect about it. So what we did now was, our first step within DeepCode was we needed to be able to unlock this big code, but in a way that is not simply treating the code as text. We want to treat the code as code. We want to, so to say, bring it into an intermediate representation. Most of the time it's a graph or a tree form that reflects what the code really does. So things like the paths inside the code, data flow inside the code, how over time the elements call each other. What we did now, for example, was we added a new language. We added C++ as a language roughly like 2 months ago, 2.5 months ago. And we took over 300,000 repositories with 3.4 million files to train the system on that. And when I say 300,000 repositories, I'm not talking about the repository as it is today. I'm talking about the history of the repository. So every pull request that was done on this repository is part of this training set. So you can literally imagine on the explosion of data that comes in that you get if you start to train the system on this amount of code repositories. So we are using the changes, and what we are doing is we are getting into intermediate representations, and these are the typical intermediate representation. This is the one that we are using, event graph. The easy one that everybody knows is the abstract syntax tree. So this is one of this. There's a control flow graph that does actually more than the active syntax tree. It has more information in there. We are using the event graph that kind of combines the goodness of a lot of different forms. It is a very complex structure that we're doing there with the code, but it gives us the opportunity to follow call patterns, to follow the type of variables, the type of return variables and stuff like this. And this is the reason why we, for example, take this. So now imagine you have these hundreds of thousands of repos with hundreds of billions of pull requests. Every pull request leads to another representation as an event graph. And now you're comparing these event graphs above each other. So the first thing that we had to solve was how to make this in a very fast and very efficient way. And this is one of the things we did. We wrote our own solving mechanisms. We wrote our own software that does the whole pipeline, and the pipeline looks like this. So this is our pipeline that we're using. We're using this big code. We are parsing it into trees. We are then running through the semantic facts that we are getting out of this. We're talking here about a data log solver, which is similar to Prolog, which I just showed you, but it's a bit more specific. It's not a complete language. And then we are building our knowledge base out of this. And this knowledge base is then what we deliver, so to say, as a model to you if you are using the system, or we are hosting it also in the internet. And what we then do with any code that we are scanning is the same pipeline. So we're going through the parsing. We are starting to run our rule set against it, and then we are injecting so to say semantic facts out of the knowledge base. And I will show you what this means in a second. So this is the pipeline that we are running through, and we are pretty proud that in comparison to other tools on the market, we are up to 54 times faster than other tools on the market. And this needs to be done this fast because you want to have this kind of engine as early in the development process as possible, so that it literally can give you feedback on the code you are actively coding. Okay, when I talk about this type here, so this knowledge base, what do we mean with this knowledge base? And we are talking about an what is called an ontology here. So what we are generating is an ontology, and let me show you what I mean with this. So here we have what is called an ontology. An ontology is a definition of a body of knowledge that you are encoding. So it's a structure of knowledge, of a body of knowledge. It gives relationships, it gives entities. And what I have here is a very simple ontology on object-oriented programming languages. So what you have here is you have literally all elements that object-oriented programming is done about. So here, for example, we have a type. And these types have, let's dive into this, you know, they have wildcards, there are arrays, there are primitive types, what primitive types are there, and the type is a subclass of the primitive types and stuff like this. So this is an example of an ontology. It gives a structure on a body of knowledge. So what we can do now by using these ontologies that we generate automatically out of this training data that we get, is we can start to reason about things, and we can start to build help texts that help you to understand what the problem here is and how to mitigate the problem. And I will show you this in the tool in a second. So this is the idea. What is an ontology? Again, a data structure. It gives a structure over a body of knowledge, and we are using this to enrich the results that we have. Okay, so talked a lot about symbolic versus sub-symbolic AI, and I think the point is now, and we've seen a lot of positive reactions from companies like IBM and Facebook and Google's and with what we are doing, and they are literally moving in the same direction. I saw a guy from IBM saying that combining symbolic and sub-symbolic AI is the way forward, and it needs to be done as a kind of maybe a default in the future to push AI into the next level and to prevent what is called the next AI winter, where we end up in a kind of a one-way road or a kind of dead end with what we're currently doing in the sub-symbolic way. So here you see where we are, so to say, pushing forward, and we want to go to the lower right here with our solution. Okay, so if we are going to static code analysis, I talked a lot about some of the limitations we see. I talked about performance. I talked about recall versus precisions. What type of bugs do we have? I talked about the scaling of rules. The typical tools, rules are handmade. Every developer can do as many tools per week as a developer can do, but we need to scale exponentially. I talked about expressiveness. By using ontologies, we can actually be more expressive and show you a better explanation. Two things are coming on top of this now. And number one is polyglot. I would argue that in every project, whatever language you're using, you have JavaScript on top. So if you're having a Java or whatever project you're doing, there is some JavaScript in there, and maybe some Python, and maybe, you know, so we are ending up in a world where we have to talk several languages to understand really what the application is doing. Another thing is APIs. I think the JavaScript world is a nice example for this week's library. Yeah, so we're changing libraries super fast, and the static code tool needs to follow this and need to be able to follow the library that comes up this week. And the point that I want to make with this is if we want to understand, for example, where does user input data come in, how does it flow through the application, you need to understand where API calls are actually bringing in external data. You can do this now by hand, but obviously here we are with a linear scaling of rules. So you would like to have the system learning itself. Where does this, what is an input vector, what is a sanitation function, what is a sink in that regard, like a database query or something like this. You would like the system to learn it itself. And there are two ways of learning it. One way is the big code that I just mentioned, and the other way is actually the documentation. So one of the things we added very recently is that we are reading documentation now. So we are using the documentation, for example, for the Java environment to literally see how these classes react, how they work, what kind of return types they have, and stuff like this. So these are the limitations we see, and this is the way we want to address them. Performance, we did our own stuff here. I go over this now very fast because I want to go to the demo. And the expressiveness by using ontologies. So let's go into the demo. Let's do some deep code, and I hope I'm in time more or less. So this is the DeepCode AI website. If you want to scan code and do something, there is the dashboard. So you can log in. You can use your GitHub login, for example, to log in. And this is my dashboard now. So you see this is on GitHub, and these are my repositories that I have. What I would like to do now is I would like to use a publicly available open source repo. So there is the 3GS repo here. And as you can see, I just so to say pasted in, this is the user and the repo name, and it finds it. And now I can click on it. And I have to admit, I did this before we joined here. So you see, it's already cached. To pull the repo and to scan it was a process of roughly 3 seconds. Most of the time we use is to pull the repo. So the 10 seconds here is I think like 7-8 seconds is literally getting the repo, and then roughly 2.5 seconds or so we needed to analyze it. So now we see here what are the suggestions we find, and let's drill on this one deeper here. And what it says is we have unsanitized user input flow from the document location and is used to build a regular expression. This may result in a regular expression denial of service attack, RDoS. As a bit of a background, I can construct regular expressions that are literally looping endless. Yeah, they will consume all of your CPU and they will consume all of your memory if needed. Most regular expression libraries these days have limitation functions. So they are literally watching themselves, and if the regex takes too long to be evaluated, it stops it and returns an error or throws an exception because of this. And if you go here on the more info, you can actually see the OWASP article that shows this. So here comes the ontology. Yeah. So here with this more information, with this text that we have here, the system is trying to give you as good information, as good argument and reasoning about the problem that we see here as possible. So let's have a look into it to simply see if it works out what it says here. So here it flows in. It says filter input.value.trim in the document location. We'll look at this later, and it says the regex here. So here here v is set to this, and then here v is used to build a regular expression. Okay, so this is the one side of it, and it comes from the document location. So return window document location. Okay, so how does extract query now end up in filter input value? So how does this connect? And the point is now, if we go to extract query, we just do this and we search for it. So Control F, you see it's twice. If we go up, you see filter input value is actually equal to extract query. So what the system did is it followed the data flow through the whole file here and found out that in this data flow, this variable was actually assigned to that variable, and that variable was tainted. It came from external and it needed to be sanitized before we can use it. So how can we, so to say, fix this now? And we have some ideas how you can fix this. Yes, there are some examples that we found in the open source world, how these guys were literally sanitizing the external input before using it. And this is what, again, the ontology helps us to say compile for you in this regard, to give you an idea and an understanding. The ontology also helps us to define the tags. You know, where does this come from? Is this a security problem? Stuff like this. All of this comes from this ontology knowledge base that is behind it. So just to show you how this works, I would like to invite you to it yourself. So if you log in to the dashboard that I just showed you here, if you put any Git URL up here, you can search for any open source stuff and simply see how it does, see the feedback it gets out of the system, and you can play around with it and see if things make sense for you. Okay, woohoo! With this, I'm with my call to action. So if you use static program analysis, and I saw statistics in the Java world, which really made me curious. You know, there's a statistic in the Java world that literally said 30% of all Java developers actually don't use it, which is a kind of a So if you're using program analysis, and there's a lot of good stuff out there, a lot of good tools out there, including DeepCode, always revisit your tool stack, always optimize your tool stack. It's a very valuable part of the tool stack to have static program analysis. If you're not using it, you're part of the 30% that I just mentioned. It's okay, yeah, you're amongst friends. We know where you come from. Try some tools. For the Java developers, I'm pretty sure there's some IntelliJ left and right. IntelliJ comes with a big collection of static program analysis tools already. Do that, use that. If you are in other worlds, you have other tools, other IDEs, for sure you will find something there. What I also would like to ask you is give DeepCode a try. See, so to say, the difference that we can make between the tools that are there already and the new way from us of doing things. What we are currently seeing is that we gain a lot of performance of how should I say, velocity out of the way we're doing things by using training to set up the rules and coming up with the rules. So it took us 2.5 months, 3 months to support C++, from literally nothing to C++. We have some more things in the pipeline. I'm not allowed to talk about now, but there are, like, in 2 months, 3 months, you will see that there's more stuff to come, where we currently use our engine to go even beyond what the others have. As of now, I would say we are already with a very small team. You have seen all of the people. We are on par with what there is from even the biggest companies out there. But I think we just got started. So there is a lot of more to come in the near future. Good. That was my presentation so far. I was trying to be fast and good. I saw a lot of questions already coming in. So shall we go for the questions?
Yeah. So thank you so much. It was quite an amazing presentation, and I think a lot of the attendees will agree with that. You know, one thing about rule-based, you know, the whole rule-based approach, right, has been sort of neglected And to a large extent, I mean, if you think about it, rule-based systems work really well with closed systems, and programming languages are closer to closed systems than, say, natural language.
Yes.
And that's the reason why natural language it makes sense, for you to use things like your word embeddings and that kind of stuff, where you have some level of ability to deal with new information coming in, right? And you are also sort of tolerant for some level of inaccuracy, but code you can't. You really have to have a lot more rigor and explainability in that, right? So one question that I think R2 and then Mohammed were in the audience were sort of asking and debating is, so we I think most of us or a lot of us understand, like, in neural networks or typical machine learning, the kind of training that supervised training that we do. But for deep code, right? Because it is a symbolic AI, traditional symbolic AI systems, you encode the entire rule base and knowledge base, right? So where does the training come from? Is it similar, or is it a different animal altogether?
I would say there are similar parts and there are different parts. So the similar parts are actually that we so I showed you the taint analysis. I showed you where we trace data flowing through the application from an outside source into an intern sink and searching for sanitation in the middle, so to say. So what we have now is we have a rule that describes this kind of a process, that external data comes in, it is handed over inside of your application and then ends up in a sink. And what we are searching for is the sanitation in the middle. Now, what would you, in classical world, what you would have to do is you would have to define in the knowledge base, this is a sanitation function and this is a sanitation function. Yeah, you would have to encode the knowledge in a way. This you have to encode the fact. The fact, this is a sanitation function. What we're doing here is we're actually using the machine learning part to encode these facts. So we are literally going out and saying we are actively searching using the patterns that we have. We are searching for changes in code that were done where the intermediate representation before the change and the intermediate representation after the change show that they introduced sanitation into that. And then we are looking into how did they sanitize it? Is there a kind of a common pattern in the sanitation? The easiest way is that we find a new function, like sanitize this. That would be the easiest way, but most of the time you have a combination of things that they're doing to literally sanitize. And then we start to see like patterns emerging, sanitation patterns that they're using on certain types, for example. And here, that in that regard, I would say that is very, a typical machine learning, so to say, approach that we are taking there.
So it's a bit like what we do in feature engineering, where you pass in a lot of data, do some kind of analysis or some kind of statistical analysis, and sort of figure out, looking for the patterns, or maybe something like topic modeling, right, where you pass it through an algorithm and then you're trying to figure out the patterns and then figure out the rules using those patterns.
Exactly. Yes.
I see. Okay, yes. That's very, very interesting.
Yeah. And what we also did was we looked into the way to so to say interpret an intermediate representation backwards, to how can we get from the intermediate representation that we have into code again. And this is something where we see there's a very strong limitation currently on the machine learning side of that, because there are several ways to codify the same graph that ends up in the same graph if you so to say optimize the graph. Yeah, but there are several ways of doing this, ending up in the same graph, and then we end up with should I say artifacts, you know, where the several ways that we have overlay each other, and instead of choosing the real one of them, we are actually seeing like a combination of some of them, which makes the code illegal. So this is something where we also looked into, and we draw some of these things out to like for future products that we want to see, but also for how we are using our own machine learning system. So how we feed our machine learning in that regard to sanitize the data in certain aspects. Yeah, so I think there is a combination of the two. There is some aspects that are kind of on the leading edge, and there are some aspects that are, I would say, pretty typical. So we are using a lot of support vector machines, for example. It does not always need to be the neural network in that regard.
Right. Use whatever tool that makes sense.
Exactly. Yeah.
Okay, next question from R2. Do you know of any study that compares bug rates in different programming languages? If so, what languages have programs with the fewest bugs, and which languages have the most?
That was actually one of the questions I was about to say naively asked, but let me explain what I mean with this. When I joined DeepCode, because I said the same thing. You know, is there a language that is kind of error prone? And you see a lot of discussion currently going on about C++ moving to Rust because C++ is so error prone and Rust is so better. I saw yesterday the reaction of Bjarne Strostrup about it. Number one, you need to be aware that bugs, a bug is not like a simple thing. A bug has a certain severity to it, and a bug is something you cannot simply sort of say count as one in this regard. You have to see the spectrum that there is. There are some bugs that are simply not so nice, and there are some bugs that are literally like security issues or crashes or something like that. So that is one of the dimensions that you have to see. Another thing is that literally with every development language, you can produce good code, but some languages have a more mature ecosystem than others. Some languages produce enormous amounts of more code than others. So some languages are used in different contexts. So if you look at C++, I would say a memory bug in C++ is probably more severe than something. Okay, let's be a bit harsh, and that's something in Python, for example, because Python is on a higher abstraction layer. There's so many things underneath it that will catch issues that you have and be graceful with things, while in C++ it might simply end in freezing your machine. So this is the dimension that we see there. There is some research about this. You can find it from NIST, for example. So NIST and the NSA did studies on static program analysis, on how tools, so to say, compare in static program analysis, and they did also some study on the comparison of bugs in different languages. You can find it on the NIST page. I can find it and send you the link if you want. There is some study on this. We are very careful in that regard. So we wouldn't say, C++ is error prone, don't touch it. Rust is much better, because that is too simple of an equation, if this makes sense. But there was some research. There's some data available, and you can see this on the NIST homepage. I hope this answers the question.
Yeah, there was also a very interesting article. I think it came out from Google. I think it was Google Home. They said that when they moved from Java to Kotlin, the NPEs, right, the null pointer exceptions, fell like 33% or something like that. So, you know, as languages become more advanced, you know, definitely there'll be all these safety nets being built so that, you know, we don't have a lot of dumbass kind of, you know, beginner developer kind of issues cropping up, right?
On the flip side, and I think that is, I mean, it's a very valuable discussion. I think on the flip side, I know that the Eurofighter, yeah, the jet, the software was developed in ADA, and the reason for that was that they said ADA is pressing you into a very clear structure on the return types and all of these things. The problem now is how performant are you? How good are you? You know, cranking out ADA code.
Yep.
How fast does this go? How is the tool ecosystem there? How many developers do you find literally being able to do ADA and stuff like this? So this is the balance that you have to come up with, I think. You know, and I think we all agree that in JavaScript you find awful code in JavaScript, but still it's making big inroads currently. You know, now we are trying to nail with TypeScript and things. We are trying to hunt after it. You know, but I think there is more to this than simply saying what is the best language that there is in this regard. You also have to see other aspects around it. That is the point that I wanted to make. I hope it makes sense. So
right.
Yep.
Okay. Next question. So this is from R2 again. In the Infer, the Facebook Infer example, would code path coverage be a good approach to notice whether you have a test for when, say, C move to first is false?
Yes. Yeah. And this is exactly what we're doing. What you see here in a way is that we are literally going through every, so to say, possible path the code could have, and finding out that one of these paths actually leads to a illegal situation, a null dereference, and that is exactly what you see here. It's a path related analysis that is done here. So yes, this is literally what happens under the hood in that regard.
Okay, next question. So again for R2, did DeepCode download 300K repositories from GitHub? How much data in bytes was that?
I think we are close to the terabyte now. I have to admit I'm not quite sure how the current training set looks like, because it's changing over time, and we are also having different training sets for the different languages. So C++, Python, JavaScript, TypeScript, they have different training sets, and they all combined of them, yes, we get in the terabytes. I know that we just bought a new SSD, which was not easily available. We needed a really big one, and that SSD is for hosting these repositories. Yeah, it's massive. It's massive, and it's also that we are doing these change sets. So the point is that we're downloading the code on the one side, but then we have to expand the code into these different pull requests, so that you have the repos in the different versions that we then can work on to generate the intermediate representation. So even the download size is not that big. It ends up to be very big if we expand it and run the system over it. The interesting part on the flip side is now DeepCode itself. So our shipping vehicle, if you want to run DeepCode in your own environment, we offer a Docker container. So you can literally run a Docker container in your own environment, doesn't need to have any internet connection whatsoever. It's just like a local installation of DeepCode. And that actually is very small then. So the trained system the ontology and all of that stuff literally boils down to, I think, 4 gigs or 5 gigs or something like this. This is all there is. The training data is massive, obviously.
Got it. Got it. Okay, the next question again is from R2. So the first line in DeepCode homepage says DeepCode is fully free to support the global community. So how does DeepCode make money?
So our business model is that we are saying, number one, we want to be free for open source forever. And this is part of the, so to say, part of the business model, and is encoded in the business model. So open source will always have free access to DeepCode. What we are currently doing is saying for small teams, and we are defining small teams like teams to, in COVID time, up to 30 people now. We are also free for these teams, and we are working with team sizes larger than 30 on like an enterprise level. So we have enterprise customers, big electronic companies, big software companies, and they are looking into using DeepCode on their whole infrastructure, sometimes like several thousand developers that we have there. So there we make our money. The next part that we are doing for them is that we also offer for these large customers to train on their own infrastructure, on their own code base. So you have these companies, they have literally hundreds of millions of lines of code, if you see the change sets, with very big projects. And we are offering them to literally use the same mechanism to use open source, but also use their internal source, training on them, and then generating rules for their internal code representation that is kind of unique to their code. And there we're also charging money. So this is the way we are, so to say, making money, and this is the business model that we have currently.
Right, right. So, for example, like insurance or banking or healthcare, because of compliance reasons. Okay, I suppose you guys provide consultancy for that, and that is going to cost money, right?
Yes, yes, yeah. So the consultancy costs money, but also if you have like large team infrastructures, for example, healthcare or insurances, they want to host it locally in their own infrastructure. So we provide the Docker container. And in that regard, now then you are enterprise, okay? And then we send our sales guy.
Right. Okay. So I know that at least either you guys already have an integration with GitLab, or you're still working on it.
Yeah.
Oh, it's okay. So it's already working with GitLab.
Yes. So we are working with GitLab. We're working with Bitbucket, and we're working with GitHub.
Got it. So okay, I just have one last question. No, actually it's not one last question. Okay, before that last question. So okay, this is from Matthias. You talk about electronic companies you work with. Do you have in mind supporting languages like HDL, Verilog, VHDL, those kinds of languages?
Not as of now. When we are talking to these companies, we are mostly in the C++ realm. And we are talking about like their C++ code base, sometimes beginning from the operating system upwards, sometimes based on, you have like the typical embedded systems that there are, and with the embedded kernels like VxWorks and stuff like that. So this is what we're talking about currently. It would not be impossible to go into also these hardware definition and these languages that define hardware in the end. The system itself should be capable of doing this, but as of now we are focusing on the software side of the world only.
Great. So I hope this is the last question. Okay.
No problem.
So for folks here who may want to muck around with these rule-based systems, what is the framework or tool that is most current? Because I personally have worked with a rule-based framework before called Clips. I don't know if you remember that. That was a long time ago. I think it was like 1990 something. But what is the framework now? What's the tool now? You showed something earlier on. Is that the latest? Or
no, I mean that is. It's in a way the latest as it is kept current. It's kind of continuously in development. It is used a lot in academics, education, and stuff like this. But I would say, and this is probably a good way of using it. Okay, so if you want to get into this, if you want to try it out, if you want to have demos you can play around with, I think that thing that SWI is quite a good thing. In production and in real production, you find not Prolog, but you find a language that is called Datalog that is used widely in production because Datalog can be better optimized for to have a better runtime. There is an implementation that is called Soufflé of a Datalog solver that is used in production widely. So we know that Amazon, for example, is using Soufflé internally for optimizing network and yeah, so quite a lot of AWS is actually managed by Soufflé in that regard. So if you want to go into production with this, probably Soufflé would be a better way forward. We ourselves, we went beyond Soufflé. So our solver engine is homemade, homegrown. We are also using a version of Datalog, but we had even harder performance constraints, and so Soufflé didn't break it for us. We had to do our own one. But I would say learning probably this Prolog interface is a quite good way to get into it and to find out. If you want to go into production, have a look at Datalog and Soufflé. You find a lot of good content there, a lot of good training materials and stuff like this. And it is a proven system. It is used in production. For us, we even had to push further than Soufflé. I hope this answers the question.
Yep. Okay, so if there are no more questions, because it is really late for Frank. What time is it? It's like 5 a.m. or 4 a.m.
It's
now?
4:21 in the morning with me now, but I have my beach behind me. All is good.
So, if there are no more questions, I think we should let Frank go and have his breakfast, his big breakfast now.
Yeah.
So really, thank you so much. It was a fascinating
Thank you very much.
Presentation. It was really, I think a lot of us were blown away by the kind of work that you guys are doing, because not a lot of people think about symbolic AI. Everybody thinks about the standard neural networks or machine learning algorithms now. But in any case, thank you, and thanks everyone for joining. This was great. Thank you.
Thank you very much. Thank you for having me.